Let us see some of the interview questions which are asked in static timing analysis followed by synthesis roles. So if you are trying to apply for a role called as synthesis or static timing analysis, then you can expect these kind of questions. So first question, what is static timing analysis? Why is it used? So this is the answer. STA is a method to verify a design's timing without requiring simulation. It checks the timing parts, ensures setup and hold requirements are met, and identifies critical parts for performance optimization. So if you want to understand about detail of what is meant by static timing analysis and what are the inputs and outputs that are present and what kind of checks that we perform, I've made a video on it. Please check out that video in a playlist called as static timing analysis. Next, what is timing path and what are its components? So we have discussed already the 4 types of timing paths, that is input to register, register to register, register to output, and input to output. So you can see the answer here. A timing path includes, it has a start point and end point. So start point is also called as an launch point and end point is also called as an capture point. And coming to logic delay, delay through combinational cells. So if there are any combos that are present, it will have some amount of delay which contributes to logic delay. And coming to clock delay, parts of the clock signal from sources of the flip-flop. So let us try to understand it by means of an example. So you can see this particular figure. Here I have mentioned all the parts. So from input to register, this is one of the path, and from register to register, here starting point is clock and end point is data pin of flip-flop 2, and next one is register to output. So here start point is clock pin and end point is output port, and one more thing is input to output. So 4, that is input to register, register to register, register to output, and input to output. And here these gates are nothing but buffers. Here you can see this clock path. In this clock path, no clock inverters or clock buffers are present. So as of now, you can assume that at equal intervals of time, both the flip-flops F1 and F2 will receive the clock. And this is one more example where again the input to register, register to register, register to output, and input to output parts are same. But here I am adding some amount of delay. This is the capture flop, this is the launch flop. So these kind of scenarios are good in terms of setup. So this is good for setup and it will be bad for hold. So we'll be trying to understand more about this in the upcoming slides. And one more figure here, this is one more figure where it contains input to register path and register to register, register to output, followed by input to output. That's the only difference is I'm adding buffers and I'm removing buffers sometimes. So I've taken few of the scenarios. And this is one more thing, whereas simple inverters I'm using instead of buffers. Rest everything will be same. So here earlier it was buffer, now I've replaced it with inverter. The same thing is applicable here. So these are the different timing parts. And if you come into the start point, here the start point is an input and end point is data pin of flip-flop 1, and from this start point is clock, end point is data, and here start point is clock, end point is output port, and in this one starting point is input port and ending point is an output port. So that's what you can mention it here among the start points and the end points if anyone asks about what are the timing parts and what are its components. If not, you can take this overall figure. Here you can see from oscillator to clock definition point, it will have some amount of latency called as source latency, and from clock definition point to the clock pins of the flop, it is called as a network latency. This blue colored one is network latency, and here this blue colored one is network latency, whereas this red colored path indicates source latency. And this is one of the simple scenario which I have taken. So if you want total latency, it is summation of source latency plus network latency. I have made a video on this set clock latency constraint also. Please check out that videos. Next question, what is the difference between setup and hold? So we already know from the definitions of setup, it is the minimum time data should be maintained constant before the arrival of clock. So before the triggering of clock, data should be maintained constant. That is called as an setup time. Coming to the hold, after the triggering of the clock, data should be maintained constant. So that's the answer. Ensure the data is stable before the clock edge, called a setup check. If it is hold, ensure that the data remains stable after the clock edge. So from this figure you can understand here I am maintaining the data constant before the active edge of clock, called a setup time, and after the triggering of the clock I am maintaining data constant, called as an hold time. Whereas TPD is nothing but propagation delay, which is nothing but the delay from clock to Q. So from the clock triggering point to the point where we are getting the output Q. So this amount of delay is called as an TPD, which is propagation delay. So you can understand more about the setup analysis and hold analysis from these examples. So I have taken a figure which has 2 flops and some combo delay is present, and here this is the required path. This is also called as an capture clock path. So required path will have minimum amount of delay, and this is the best case scenario. Here fast corners will get applied. whereas arrival path is something which is from clock to Q delay followed by combo going to the data pin of flip-flop 2. So this is called as an arrival path, which will have maximum amount of delay in case of setup, and it is the worst case, and slow corner will get used. So this is the formula for setup, that is required time should be greater than the arrival time. And coming to the required time, here this is the required time. So this required time should be computed by means of an time period. So here it will be time period followed by some setup time. So setup time will be present between D2 and clock 2. So that's why I have taken required time is total time period minus T setup. Whereas arrival time is something clock to Q delay followed by this combo delay. So it is clock to Q delay followed by combo delay. So for setup, required time minus arrival time is the formula. So simply substitute these required times and arrival times here. So it is total time period minus T setup minus arrival time is something which is clock to Q delay plus T combo. So here the symbol will be minus. So this is the formula for setup time. And coming to the hold time, here observe this point. If it is required path, here it will be the maximum delay, which is worst case, and slow corner will get used. And whereas if it is arrival, for arrival it is min delay, best case, and fast corner. So remember this terminology carefully between setup. So for setup, generally arrival path will have max delay, whereas here it will be min delay. And coming to the formula, it is arrival time should be greater than the required time. So arrival time is something which is clock to Q delay followed by the combo delay, and required time is something which is hold time of this capture flop, which is FF2. So here replace this one with hold. So this is nothing but hold time. So hold time is clock to Q delay plus T combo minus T hold. Next question, what is clock skew? How does it affect timing? Coming to the answer, clock skew is the difference in the arrival times of the clock at different flops. So this clock can be coming from one clock source, or it can be from the different clock sources also. So like that, it can be classified into types like positive skew, negative skew, or else zero skew. So coming to the positive skew, it helps setup time, but it is worst hold time, whereas for a negative skew, it is worst setup and best hold. Next question, what is clock uncertainty? So clock uncertainty accounts for variations in clock edges due to jitter and skew. It is modeled as a timing margin during static timing analysis. So generally this uncertainty is nothing but it is summation of skew, jitter, and some margin. So if you want detailed understanding about this clock uncertainty, please check this particular constraint where I have explained in detail about what is meant by clock uncertainty. So here in Google, simply type as set underscore clock underscore uncertainty. Then you can see my particular video. It will look something like this. Next question, explain the concept of critical path. So we already know critical path is something which will have more amount of delay within our particular design. So see the answer. The critical path is the longest path in the design that determines the maximum clock frequency the chip can operate. So by using this critical path only, we will get to know about our clock frequency, and this is the path that will have highest amount of delay. Next question, what is the significance of derating factor in static timing analysis? So derating factors models pessimism or optimism in timing due to process voltage and temperature variations. So generally derating is done to add delay or to subtract delay, like it will be simply plus or minus. So the constraint that is used is set underscore timing underscore derate. Coming to next question, what is meant by clock latency? So I already told you, like latency are classified into two types, that is source latency and network latency. You can see from this particular figure, from the PLL, that is from the point where the clock gets generated to the clock definition point, also called as a clock port, it is called as source latency, and from the clock definition point to the clock pin, it is called as network latency. So that's what I mentioned it here. Source latency means time for the clock signal to propagate from the clock source to the clock definition point, whereas network latency is something delay introduced by the clock tree, or else it will be from the clock port to the clock pin of the flip flop. So if you want a detailed understanding of this clock latency, I have made a video on this also. So if you search in Google as set clock latency, you will get these two videos. Please go through these two for more understanding. So it's the overall figure looks something like this. From the oscillator, means this is the point where the clocks get generated, to the clock definition point called as source latency, whereas this is the network latency from clock port to the clock pin of flop. So this is also from clock port to clock pin of the flop. So simply total latency or total delay, or else you can call it as simply clock network delay is nothing but summation of source latency and network latency. This network latency is also called as an insertion delay. Remember this point. Next question, how do you handle false path in static timing analysis? So generally this false path, if you want to set any path as a false path, you have to use this particular HDC constraints called as set false path to exclude unrealistic timing paths from analysis. So I have made a detailed video on this set false path also. Please check this, and this is a link which I have mentioned it here, and this is my channel name. Next, what are multi-cycle paths and how are they modeled? Multi-cycle paths are designed to take more than one clock cycle for data propagation and it is set by using set multi-cycle path. Generally, our data should reach to the capture flop within one clock cycle. Suppose if it is taking more than one clock cycle, then we have to set it by means of a constraint called a set multi-cycle path. Next question, how does static timing analysis handles asynchronous clock domains? So in order to understand more about this, you need to understand about set clock groups. So I have made a detailed video on the set clock groups also. So please go through this so that you can answer this question easily. So by defining asynchronous clock groups with set clock groups hyphen asynchronous. So simply asynchronous is something like those two clocks will not be synchronous. Means those two clocks, that is clock 1 and clock 2, they are getting generated from two different sources. So that's why those two are asynchronous. And generally infinite timing window is used in order to compute this one. Next question, what is hold time violation? How do you fix it? So this is one of the important and the common question that is asked in the interviews, like how will you fix hold time violations, or else how will you fix setup time violations? So you can check out my Instagram page. So here my Instagram page name is VLSI.tmsy tutorials. So simply you go through that particular page where I have mentioned all the synthesis and static timing analysis interviews, questions and answers, and it looks something like this. So now let us see what are hold timing violations. So hold timing violations and how we can fix it. So to fix hold violations, first concept is downsizing the cell. So downsizing the cell is one of the concepts. So upsizing is nothing but increasing the drive strength, whereas downsizing means we are reducing the drive strength. And one more thing is VT swapping from LVT to HVT. So lower threshold voltage to higher threshold voltage. Why? Because for hold, arrival time should be greater than the required time. If arrival time should be more, then obviously delay should be more within that particular arrival. So that's why if there are any LVT cells, simply replace it with HVT cells. And one more, this is important concept like pulling and pushing. Why? Because in our hold concept, arrival time should be greater than the required time. As arrival time should be more, pushing the launch clock is important. As we are reducing the required time, pulling the capture clock is important. So remember this. As arrival time is more, so simply we are pushing the launch clock. So thereby delay gets increased. Whereas required time should be less than the arrival time, right? So that's why we are pulling the capture clock. So delay will become less. And one more thing is inserting buffers at the D pin and metal width decreasing. So generally, if you are taking any metal stack from M1 to M9, if you are going up the metal stack, the M9 will have less amount of resistance compared to M1. Whereas if it is metal M1, it will have more amount of resistance. If it is more amount of resistance, then obviously delay will be more. So that's why metal width we are decreasing. Next concept is net deteriorate. Next one, using spare cells after BTO. Here BTO is something called as base tape out. And one more thing is inserting metal buffers after base tape out. And next one is voltage can be reduced. So these are some of the hold fixes. And you can see here, hold is something which is calculated at the same edge, whereas setup is something which is captured at the next edge. Next question, what is setup time violation and how do you fix it? So setup time violation occurs if a data is not stable before the capture edge, fixing it by optimizing logic or reducing clock frequency. So let us see some of the setup time fixes. So these are some of the setup timing fixes. So upsizing the cell. So upsizing the cell means drive strength will get increased. If drive strength is getting increased, then delay will be less. Next one is VT swapping from HVT to LVT. So higher threshold voltage and lower threshold voltage. So we are coming to LVT cells so that switching will be faster. Next one, in setup, remember the condition like required time should be greater than the arrival time. So here as required time should be more. So if required time should be more, then capture clock delay should be more. So that's why we are pushing the capture clock. Whereas required time is greater than the arrival time, meaning that arrival time will be less. So if arrival time is less, then simply pull the launch clock. So don't get confused between these 2 points. So pulling the launch clock and pushing the capture clock in case of setup. Next, inserting buffers when the net is dominant. So whenever long nets are there, so in order to break that one, or else in order to reduce the delay, simply add buffers. So what will happen is if you are adding buffers, then the transition which is taking more amount of time will get reduced. So that's the importance of adding buffers. Next, metal width is increased. As I told you, if you are taking a metal stack from M1 to M9, M9 will be having less amount of resistance, whereas M1 will have high amount of resistance. So if resistance is more, obviously the flow of current will be less. If the flow of current is very less, then delay will be more. So here we are increasing the metal width. So we are, instead of M1, we are going for M9. Let us take some of the example called as an M9. Next one is metal jogging from lower metal to higher metal. Next, use of spare cells after base tape out. Next, we can use metal buffers after base tape out when net is dominant and frequency can be reduced. So this is the last step. Generally, we should not touch the frequency if you are getting any setup violations. And this is how it is calculated. Hold is calculated at the same edge and setup at the next edge. So that's why setup clock it is launching at 0 and capturing at 10, whereas hold is at same edge, that is 0 and 0. Next, what is the difference between pessimism and optimism in STA? So generally in VLSI industry, these two terms are commonly used, like pessimism and optimism. So better to understand the differences between pessimism and optimism. So pessimism, it assumes worst case condition, whereas optimism means it is ideal condition. Next, what is recovery and removal checks? So recovery and removal checks, these are something which are done with respect to clock followed by asynchronous pins called as set or reset. So recovery is similar to setup and removal is similar to hold. So it is a minimum time the data should be maintained constant before the arrival of clock. We know from the setup, like it is a minimum time data should be maintained constant before the arrival of clock. Whereas in case of recovery, it is a minimum time the set or reset pin should be maintained constant before the arrival of clock. Whereas removal is something like minimum time the set or reset pin data should be maintained constant after the arrival of clock. So simply in setup, we will make use of data at the D pin, whereas in case of recovery and removal, we will use either set or reset pins, which are nothing but asynchronous pins with respect to clock. That's the only difference. Setup and hold checks are done between data pin and the clock pin, whereas recovery and removal are something which are done between asynchronous pins followed by the clock. Remember this simple difference. Next question, what is max transition and max capacitance? So max transition means it is an upper limit on signal transition time, whereas max capacitance means upper limit on load capacitance of a net. Next, what is OCV, which is called as an on-chip variation? OCV models timing variations due to different delays within the same chip. So you have to understand in detail about this concept called as an on-chip variation. There can be variations because of process, voltage and temperature. So this is a big concept. Please go through that on-chip variation concept. Next, what are setup and hold margins? These are safety margins added to account for variations like jitter, skew and process drift. Next, what is the difference between WNS and TNS? WNS is worst negative slack, TNS is total negative slack. So total negative slack is simply the summation of worst negative slack. So you can see here worst negative slack means the worst timing violations in a path, whereas TNS means sum of all negative slack across all failing paths. Next, what is PBA? That is path based analysis. PBA calculates delays for each timing path individually for more accurate slack values. There will be one more thing called as graph based analysis, that is GBA. So in graph based analysis, generally high slew value will be used, that is worst condition, that is used for worst case condition, whereas PBA is something which is best case condition. It will make use of actual slews, whereas graph based analysis will use a maximum slew from the dot lib. Next, what is crosstalk noise in static timing analysis? This is one of the important concepts. Like whenever two wires are present parallelly, there will be a problem of crosstalk. So again here different scenarios will be there, like about the aggressor and victim. I will explain more detail about this crosstalk in my upcoming videos. So as of now, coming to the answer, signal interference between adjacent nets causing delays or functional errors is called as an crosstalk. Next question, how is derating applied to timing parts? So as we have already seen this one, we have to use a constraint called as set timing derate to apply factors for early and late variations. So it should be applied with respect to clock path and data path. I mean hyphen clock and hyphen data switches should be used. Next, what is the difference between ideal and practical clocks in static timing analysis? So ideal clock is something which will take zero amount of delay to transition from 0 to 1. That is no delay, it assumes perfect arrival. Whereas propagated clocks means delays are modeled for real world behavior, means it will take some amount of time to move from 0 to 1, means some amount of delay will be present. It will have some amount of transition time. So if you want to know in detail about this, please go through this video. I have made a video on ideal clock, practical clock, duty cycle and transition. Next, how do you handle clock gating in static timing analysis? Generally, this clock gating is used in order to turn off the clock to the particular design, whichever or whenever it is not in use. Why? Because to save power consumption. I mean, for the sake of power consumption, we go for this particular concept called as clock gating. Gating means we are simply cutting off the clock whenever it is not in use. So it can be done by using either an AND gate or by means of an latch. So analyze enable parts to ensure no setup and hold violations occur during gating. Next, what are ECOs and how are they handled in static timing analysis? ECO is something called as an engineering change order. It involves timing fixes post layout using minimal changes. If you are having any amount of issue with either setup or hold, or else if some delay should be increased in some path or else it should be decreased in certain path, then we go for ECOs. So here there is one command called as an ECO change cell. So let me show you that one. So this is my Instagram page called as vlsi.tmsy.tutorials. So here you can see all the interview questions and answers. So let me show you that ECO change cell. So you can see here I have mentioned one scenario where suppose if you want to make any ECO changes, you can use two commands called as ECO change cell followed by the instance name followed by the cell name. This is one thing, or else you can go for change cell hyphen instance name followed by hyphen cell. So in this manner you can experiment to replace a particular cell within your timing path. So here you can see the instance name, these are the args, these are the cells. So if it is contributing to more amount of delay, you can use this particular command called as ECO change cell or else change cell in order to replace these existing cells with different cells so that you can fix setup and hold violations. So please follow this page if you want more updates regarding interview questions on synthesis and static timing analysis. So thank you.